Welcome dear audience, students and scholars. Here I am Dr. Amjad Ali. In this video we will learn about technological progress in the Solow model. Dear scholar, with the basic version of Solow growth model as our starting point, we take on 4 new tasks. Our first task is to make the Solow model more general and realistic. In classical model we saw that capital, labor and technology are the key determinants of a nation's production of goods and services. We developed the Solow model to show how changes in capital through saving and investment and changes in the labor force through population growth affects economy's output. We are now ready to add the third source of growth, changes in technology, to the production mix. The Solow model does not explain technological progress, but instead it takes it as exogenously given and shows how it interacts with other variables in the process of economic growth. Our second task is to move from theory to empirics, that is, we consider how well the Solow model fits and effects. Over the past 2 decades, a large literature has examined the predictions of the Solow model and other models of economic growth. It turns out that the glass is both half full and half empty. The Solow model can shed light on international growth experience, but it is not far from the last word on this subject. Our third task is to examine how a nation's public policy can influence the level and growth of its citizens' standard of living. In particular, we address 5 questions. Should our society save more or less? How can policy influence the rate of saving? Are there some types of investment that policy should especially encourage? What institutions ensure that economy's resources are put to their best use? How can policy increase the rate of technological progress? The Solow growth model provides the theoretical framework within which we consider these policy issues. Our fourth and final task is to consider what the Solow model leaves out. As we have discussed previously, models help us understand to the world of simplification after completing an analysis of the model. Therefore, it is important to consider whether we have oversimplified the matters or we have undersimplified the matter. While talking about the technological progress in the Solow model, so far we have discussed that Solow model assumed an unchanging relationship between the inputs of capital and labor and output of goods and services. Yet the model can be modified to include exogenous technological progress which over time expands society's production capabilities. Efficiency of labor. To incorporate technological progress, let's return to the production function that relates total capital K and total labor L to total output Y. Thus far, the production function has been Y is equal to function of capital and labor. Now we can write the production function as output depends on capital and L cross E. Here we have L labor force and E. Here we have the E efficiency of labor. Okay, the efficiency of labor is meant to reflect society's knowledge about production methods. As the available technology improves, the efficiency of labor rises and each hour of work contributes most to the production of goods and services. For instance, the efficiency of labor rose when assembly line production transformed the manufacturing in the early 20th century, and it rose again when computerization was introduced in the late 20th century. The efficiency of labor also rises when there are improvements in the health, education, or skill of the labor force. Here we have another concept, that effective number of workers. The term L cross E, or L multiplied by E, can be interpreted as measuring the effective number of workers. It takes into account the number of actual workers, L, and efficiency of each worker, E. In other words, L measures the number of workers in the workforce, whereas L cross E measures both the workers and the technology with which the typical worker comes from or comes equipped. This new production function states that the total output Y depends on inputs of K capital and effective workers, L cross E. Okay, the essence of this approach to modeling technological progress is that increases in the efficiency of labor E are analogous to increases in the labor force L. Okay, suppose for example that an advance in the production method make the efficiency of labor E double between 1980s and 2010. This means that a single worker in 2010 is in effect as productive as two workers were in 1980. That is, even if the actual number of workers L stays the same from 1980 to 2010, the effective number of workers here we have L cross E doubles, and the economy benefit from the increased production of goods and services. Okay, labor augmenting technological progress. The simplest assumption about technological progress is that it causes the efficiency of labor E to grow at some constant rate G. Okay, for example, if G is equal to 0.02, then each unit of labor becomes 2% more efficient each year. Output increases as if the labor force had increased by 2% more than it really did. Okay, this form of technological progress is called labor augmenting, and G is called the rate of augmenting labor augmenting technological progress, because the labor force L is growing at rate N and efficiency of each unit of labor E is growing at the rate G. The effective number of workers L cross E is growing at rate N plus G. Okay, the steady state with technological progress, because technological progress is modeled here as labor augmenting, it fits into the model in much the same way as the population growth. Technological progress does not cause the actual number of workers to increase, but because each worker is in fact come with more unit of labor over time, technological progress causes the effective number of workers to increase. Thus, the analytic tool to study the Solow model with population growth are easily adopted to studying the Solow model with labor augmenting technological progress. We begin by reconsidering our notation. Previously, when there was no technological progress, we analyzed the economy in terms of quantities per worker. Now we can generalize the approach by analyzing the economy in terms of quantities per effective workers. Now we have here, let's suppose that K is equal to K over L cross E. Here we have K in lowercase and we have the K in uppercase divided by labor plus multiplied by efficiency. This notation stands for the capital per effective worker, and we have the output per effective worker is equal to Y divided by L cross E, stand for the output per effective worker. With these definitions, we can again rewrite our production function Y in lowercase. We have here denoted that output per effective worker. Previously, we have interpreted as output per worker, but here we are interpreting as output per effective worker. Y is equal to capital per effective worker. Okay, then our analysis of the economies proceed just as it did when we examine population growth. The equation showing the evolution of K over time becomes as delta K is equal to SFK minus delta plus N plus G into K. We have given the detailed explanation what is the difference between this delta and this delta. Okay, the change in the capital stock delta K equals the investment. This part representing the investment per worker minus break even investment. This is our break-even investment. We can interpret this part as break-even investment. Delta plus N plus G K is our break-even investment. Okay, now, however, because K is equal to K over L cross E, break-even investment includes three terms. To keep K constant, delta K is needed to replace depreciating capital, and K is needed to provide capital for new workers, and GK is needed to provide capital for the new effective workers created by technological progress. Okay, let's see a graphical presentation that how technological progress work in the Solow growth model. So here we have the technological progress and the Solow growth model. We have capital per effective worker K on x-axis, and we have investment, break-even investment on y-axis, and we know that with the help of depreciation and population growth and with the technological progress, we have break-even investment, and the investment insert this break-even investment at this point, and this is our steady state capital point. This is our steady state capital point. So these figures reveal that labor augmenting technological progress at rate G enters into our model here. Then our Solow growth model is much as same way as we did in our population growth as by adding population and depreciation rate. Now that K is defined as the amount of capital per effective worker increases the effective number of workers because the technological progress tend to decrease K in the steady state investment SFK exactly offsets the reduction in K attributable to depreciation, population growth and technological progress. So overall this figures explain the inclusion of technological progress does not substantially alter our steady state situation. There is one level of capital that is denoted by K static, at which capital per effective worker and output per effective workers are constant. As before, this steady state represents the long run equilibrium of the economy. The effects of technological progress. Okay, from this information, it can also infer what is happening to variables that are not expressed in units per effective workers. For instance, consider output per actual worker Y divided by K, Y divided by L is equal to Y cross E. Because Y is constant in the steady state and E is growing at rate G, output per worker must also be growing at rate G in the steady state. Okay, similarly, the economy's total output is Y is equal to Y cross into L, E cross L, because Y is constant in the steady state and E is growing at rate G and L is growing at rate N. Total output grows at rate N plus G in the steady state. With the addition of technological progress, our model can finally explain the sustained increase in standards of living that we observe. That is, we have shown that technological progress can lead to sustained growth in output per worker. By contrast, a high rate of saving leads to a high rate of growth only until steady state is reached. Okay, once the economy is in steady state, the rate of growth of output per worker depends only on the rate of technological progress. According to the Solow model, only technological progress can explain sustained growth and persistently rising living standard. The steady state growth rate in the Solow model with technological progress. Here are some symbols and notations for that. We have capital per effective worker, K is equal to K over E cross L. Normally at steady state it is 0, and output per effective worker Y is equal to Y divided by E cross L, or we can write it is equal to Y is equal to function of lowercase k. At steady state its growth rate is 0. Output per worker Y over L is equal to Y cross E, and that output per worker has growth rate at a constant or increasing growth rate at G. Total output Y is equal to Y cross or multiply by into E cross L, and we have the steady state growth rate N plus G. The golden rule. The introduction of technological progress also modifies the criterion for the golden rule. The golden rule level of capital is now defined as the steady state that maximizes the consumption per worker or consumption per effective worker, following the same arguments that we have used before, it can show that steady state consumption per effective worker is C static is equal to Fk static minus delta plus N plus G into K static. Okay, steady state consumption is maximized if MPK is equal to delta plus N plus G, or we can write it as MPK minus delta is equal to N plus G. So here we know that MPK is the marginal productivity of capital minus depreciation is equal to N, we have the population growth, and plus G, we have the technological progress or technological growth, and that is at the golden rule level of capital, the net marginal product of capital MPK minus delta equals the rate of growth of total output. Here we have N plus G, because actual economies experience both population growth and technological progress at the same time. We must use this criterion to evaluate whether they have more or less capital than they would at the golden rule steady state. So this is all about the technological progress in the Solow growth model. So see you with another video. Ciao.